Okay, so let's start going over number one. Number one is purely a power rule problem, but we want to make sure that we fulfill all of our power rule conditions. So variable have to be in the numerator, radicals need to be converted to rational exponents, and we have to make sure that all of our parentheses are resolved. Okay, so we have to expand everything out. Okay, so I'm going to start distributing through. Maybe it's helpful to get that square root of x to be x to the 1/2. And I'm not going to focus on the derivative until every term is set up and ready for me to do so. Okay, so I got to add exponents, right? 3 plus 1/2, same thing as 6/2 plus 1/2, so 7/2. Okay, next term. This term is set up and ready to go, but visually, if it helps you, we'd like to push any coefficients out in front, so we don't have to look at a denominator term below the variable. Next two terms are ready to go, no issues there. Cube root of x, I have to write that as a rational exponent, so x to the 1/3. And finally, we have this troublesome expression, which is going to be radical converted to be, we know that square root of x to the 7th is really x to the 7/2. Okay. Now, when we convert it to rational exponent, that's good, but we also have to bring it up. But just know that this x to the 7/2 is next to the 2, but is not necessarily connected in a way that we have them, these don't have to be together. Does that make any sense? So I'm going to bring the x to the 7/2 up, but the 2 is going to stay in the denominator. Okay. So this is all part of the cleanup process here. Okay, any questions so far? Yeah, so the mistakes that I see with this term over the years, either students write out the term incorrectly as 1/7 or 2/7 or something, or they write it out, but then they do power rule without bringing it up to the top, or they feel like the 2 has to come along with it, so they bring the 2 up, they make it 10x to the negative 7/2. So just to point out a lot of things that I've seen over the years with especially problems like this, where there's multiple things that can go wrong.
How did you get the 7/2 for the first one?
Okay, how do we get that 7/2? Now we understand. Let me show us something that we do understand here. Square root of x. What's square root of x equal to? It's x to the 1/2, and the reason why it's x to the 1/2 is because there are some hidden numbers that we don't see. Right? There's a 1. And there's a 2. The 1 is exponent, and this is square root, so it's radical 2. So that's why we have a hidden number also here as well. Square root of x to the 7th is x to the 7/2. Okay. All right, so now we're ready for power rule. Bring down the exponent, subtract 1 from the exponent. All right, we're subtracting 1 from the exponent. I bring down the 7/2. 7/2 times 7 is 49/2. 7/2 minus 2/2, or 7/2 minus 1 is 5/2. Power rule, bring down the 3, subtract 1 from the exponent. Continue through, bring down the 2. 4 pi x, same thing as 4x. If I asked you for the derivative of 4x, you would say 4. So because that's x to the first power. We know when we find the derivative, all we're left is the coefficient in front. 5 pi to the fourth, this is a little misleading. This looks like we do power rule here, but pi is just a number. So this is 5 times 3 to the fourth, or 3.14 to the fourth. That's just a large number. And we know that's a constant, so a constant's derivative is 0, right? If you were to graph a constant, that's just going to be a horizontal line. Horizontal line has no slope, or slope 0. Okay, power rule here, bring down the 1/3. Subtract 1 from the exponent, so minus 2 over 2. Bring down the 7 halves. 7 halves times 5 halves is 35 halves. And then we subtract 1 from the exponent, so minus 2 over 2. Whoops, over 4.
Also, it should be negative
2/3.
instead of negative 1/3, it should be 2.
Oh, yeah, sorry. I didn't have the correct denominator. Okay, so we have our derivative, but we still have to do a little bit more cleanup, right? So no negative exponents in our answer. The first set of terms are good. It's just the last set right here. We want to bring these x's down to the denominator, share the denominator space with these values in the denominator. So y prime. Now, you can interchange them here. dy dx is the notation for y prime. Okay. The x comes down. Okay, any questions with number 1? Okay, number 2. We have our function x squared over x minus 1. Find f prime. Once we find f prime, we're going to find the tangent line equation. So before we can get to the tangent line equation, we need to get to the derivative. To get to the derivative, what method is involved here? Numerator, denominator, we have to use what? Quotient rule. Yeah, okay. No problem. I got handouts there.
Thank you.
Numerator, I'm going to call f. Denominator, I'll call g. Okay, so f prime, I'm going to figure out the derivative of the numerator term. That's what it's asking for, 2x. G is the original denominator. Back to f, no changes. And then g prime is the denominator's derivative. Don't forget, there's a denominator portion of quotient rule, so denominator might x minus 1 squared. I'll do a little bit of cleanup. Careful that we don't do cleanup the wrong way. You can't just cancel these x minus 1s out. Can't cancel across addition or subtraction. So I'm just going to distribute, combine like terms, and try to get that f prime cleaned up a little bit more. Denominator, leave it in factor form. This is a good place to be. So we don't want to try to expand that. Factor form is good for the denominator. All right, so I have my f prime. Any questions here? All right, so now we're writing our tangent line equation. So we know that we need to gather order pair from the original function. And from the derivative, we can gather slope. Once we have our order pair and our slope, we can put it in the point slope form. Okay, so I'm trying to get my point first. Okay, so my order pair, -1, -2. Next up, I want to find my slope. Slope comes from the derivative. Derivative takes in the x value. One plus 2 is 3. 3 over 2 squared is 4. Okay. I have my order pair. I have my slope. Now dump into the point slope form. Okay, any questions here?
Where'd you get -1/2?
Oh, the -1/2 came from the original function. Because I have to insert -1 into the original function to get the y value of my point. Okay, any questions here? Let me extend this question a little bit more. What if I asked, where is the slope of the graph 0? And where is the slope undefined? Slope and f prime is kind of interchangeable. So where is slope equals 0? Where is slope undefined? We know that this all comes from, these are slope related, so it has to come from the derivative. So where do we look if we want to figure out where the slope of the graph is 0? Okay, which part though? The numerator. The numerator is going to tell us where the slope of the graph is 0. But if I set the denominator equal to 0, that's going to tell me where the slope of the graph is undefined. Right? Okay, so where's the slope 0? I'll set the numerator equal to 0 of the derivative. So we can say f prime is equal to 0 when x equals 0 and when x equals 2. Where's the slope undefined? Undefined slope would mean where there's a 0 in the denominator of the derivative. So we set the denominator equal to 0. Square root both sides. X minus 1 equals 0. X equals 1. Okay, questions there? Okay, number 3, find the derivative of this function. I see two sets of parentheses. They're being multiplied with each other. I'm going to go through a product rule. So f prime g plus f g prime all over g squared. So I will assign my first set of parentheses as the f expression. I'll assign the second set of parentheses as the g expression. And I'm just going to go through product rule here. So f prime times g plus f g prime. So f prime, I'm going to go through a power rule for each of the terms. 3x squared minus, bring down the 5 halves. 5 halves times 2 is just going to be 5. Subtract 1 from the exponent. 5 halves minus 2 halves is 3 halves. The original g function unchanged. We're just going to bring that down. That's what the rule says. Plus, back to the original function, copy that down, and then g prime. So g prime, we have to go through and find the derivative of each term and insert it in this space. 2x becomes 2. 5 pi cubed, we can't do power rule here, right? This isn't 15 pi squared. The pi is just a number, so that's just a messy number, right? A constant is 0. 7 is also a constant, so both of these drop out. The only thing left is going to be a 2. Does everybody see that? Any questions about g to g prime? Okay, I'm not going to ask you to clean up, so there's no negative exponent. Oh, well, not clean up in terms of expand everything out, but maybe we can clean up within each of the terms here. I can reduce that to be 5. What if I extended this problem to say, find f prime of 1? What would you do? Substitute every x with what? With 1, right? So that's going to get you to a slope value. Okay, I probably won't be picky if I asked you for that. I won't be picky about how you clean things up, as long as you can insert values. Some variation of this would be sufficient. Okay, any questions about the first page? Okay, back page. Particle moves along the x-axis in meters so that at times t is greater than or equal to 0 in seconds. Its position is given by x of t. Find velocity and acceleration. Velocity is the first derivative of position, and acceleration is the second derivative of position. We can go through power rule. The nice thing about this setup is there's no cleanup necessary. Every term is set up and ready for power rule, so we jump into power rule. Yes. Okay, so if I started you off with the velocity function, then you can just go to part B without having to find the derivative. And then you can find the acceleration just by going one derivative down. If I give you the velocity function only, we haven't learned how to move back up the chain. So that's next semester. So this semester, we're only moving down the chain from F to F prime to F double prime. Next semester, we'll learn how to move back up from the second derivative back to the first and back to the original function. So if I give you the velocity function, I can't ask you any questions about the position because you don't know how to do that yet. Okay, part B. What's the velocity at 2 seconds? What's the acceleration at 4 seconds? We can just insert t into the appropriate functions. Include units of measure. What's our unit of measure for velocity here? Let's look again. Yeah, meters. So just pay attention, make sure that you read your directions and that you're double checking on your quiz, whatever unit is given, you want to follow with that unit. Acceleration. We can substitute 4 in for t of the acceleration function. All right, what's the unit of measure here? Meters per second, which is meters per second squared. Okay, at what times does the particle change direction? We got to be careful here because this is actually a two-part problem. Before we can figure out where the particle changed direction, we first have to figure out what? Right, where the particle is motionless, right, where the particle is at rest. So we can't answer this question in one step. We have to split it up, right? So we have to find when velocity equal to 0, find those critical points, then we have to populate them onto our velocity sign line, and then we have to test each of the subintervals of the sign line, look to see if there's a sign change, and then conclude whether there's any particle, any change in direction. Right, so multiple steps here, kind of misleading for D that it looks like just a one-step process, a couple steps here. Okay, so there's my velocity function. Let's figure out where it's stopping before we can even decide whether it can change direction or not. All right, we want to populate our velocity sign line, but do we keep both these values? There's -1 and 3 both fall in our domain. Okay, is anything that indicates whether we keep a value or not? Okay, where does it say? Yeah, t is greater than 0, right? So pay attention to your domain. If the problem says times are for all real numbers, then we would hold on to negative numbers. But here t is greater than or equal to 0, so we do have a stopping point, which means that this value will go onto our velocity sign line because we do have a stopping point, and it's going to indicate it's going to be part of our starting point for our domain potentially. So here's our velocity sign line. We want to know if we know that at t equals 3, this particle is not moving, but we don't know if it changes direction until we see there's a change in sign. Okay, so I'm going to test values in each subinterval as a testing point. I'll test 1 here, and I'll test 4. Each goes into the velocity function. I want to find v of 1. If I know the sign of v of 1, I know the behavior of the direction of motion for this entire time period. So I'm going to plug 1 into, I like to put it into the factored form. Helps me get to my sign a lot quicker rather than plugging in one term at a time. So if I plug 1 in for t, 1 minus 3 is negative, 1 plus 1 is positive, negative times positive is negative. So we know that this particle is moving left in this time interval. At 4, let's figure out what 4, if I plug 4 in for t, I get positive times positive, which is positive. So not only is the particle motionless or at rest at 3, it also changes, it's also a point of change in direction, right? Goes left, stops, turns around, goes right. That's a change in direction. If when I say the word justify, or if I ask the word why, then I'm looking for a because statement like this. Any questions so far, D? Yes. Yeah, sure. You can. Okay, for part E, at t equals 0, is the particle moving to the right or to the left? So we're talking about movement here. So how do we involve 0 in what we're trying to find here? Do we put 0 into the position, into the velocity, into the acceleration? Okay, we're talking about movement, right? We see left and right, that's all velocity related. So find v of 0. That's -9. That's less than 0. So since velocity of 0 is less than 0, particle moves left. Let me extend this question a little bit here. Part E. When does the particle move left and when does the particle move right? So based off of what we have here, when would you say the particle is moving left? From where to where? 0 to 3. Anything that we have to be careful of when we create our interval? Do I say parentheses 0 to 3? Bracket at 0 because first it's moving left and second it's part of our domain. And 0 is not a stopping point, right? The only stopping points for this object is at -1 and 3 seconds. So that means when the timer starts, this object's already moving. It's already in motion. And if I ask you to justify, you would say because v of t is less than 0. Okay, what about moving right? Three to positive infinity, both are parentheses, right? We don't want to include 3 because 3 is it's when the object is not moving. And the reasoning here is because velocity is greater than 0. Part F, find the average velocity. Careful with this problem here. Focus is on that word average. Do we use the velocity function here? No, right? We don't use velocity function. We use the position function and we find the slope between position because average velocity is defined as the change in position divided by the change in time. Average velocity is change in position over change in time. So we just find the slope between 2 points on our position function. So x of 3 minus x of 1 over 3 minus 1. If I ask you for average velocity, I have to give you 2 points, right? So we find the order pairs, or we find the positions at these times. X of 3 equals -25, x of 1 equals -9. Simply find that by inserting into the original position function. And now we're ready. -25 minus -9 over 3 minus 1. We get -16 over 2, which is -8. Yes. It's into the position. So I think that's the most common mistake that I see with students, that they want to put it into the velocity function because they see the word velocity, right? But that's not how we define average velocity. It's the change in position over change in time. Now, if I ask you what is the instantaneous velocity at just one moment in time, then you would use the velocity function. But yeah, we don't touch the velocity function, even though we see the word velocity. Okay, part G. What is the displacement of the particle from 1 to 4? Displacement is defined as final position minus initial position. We just care about where the object is at 4 seconds, where the object at 1 second, and just find that difference. X of 4 minus x of 1. It could be positive, it could be negative. We just take whatever that value gives us. X of 4 is negative 18. X of 1 is negative 9. Negative 18 minus negative 9 is negative 9. So this tells us that between 1 and 4, starting at 1 and ending at 4, this object is going to end up 9 meters to the left of where he started at t equals 1. Yes?
For displacement, you're still using the position formula, correct?
That's right. Displacement is just position. Okay. Any questions with F or G? Okay, moving on to H. What is the total distance of the particle from 1 to 4? This requires more work in the sense that we have to potentially involve t values between 1 and 4. So we definitely have to involve 1 and 4 for sure. But how do we know which other position values to involve besides 1 and 4? Where it changes direction. So we go to our velocity sign line and we see if there is any places where this object changes direction. If there's no change in direction, then we can just find that distance, and then if it's negative, we make it positive. Okay? But because there's a change in direction, we have to also involve information about the position at 3. So it's a little bit more involved because it requires more information for us to find total distance. So just like before, we can gather information from x of 1 and x of 4. X of 1 is negative 9. X of 4 is negative 18. X of 3 is negative 25. So what this is telling us is that he's starting at negative 9, he's going to negative 25, and he's going back to negative 18. So something that may help, if this feels abstract to you, go ahead and put these numbers on a number line and convince yourself how much movement is this object going to make. So if he starts at negative 9 here, he goes all the way to negative 25, and he goes back to negative 18. Okay, so let's track this object's movement. He's going from negative 9 all the way to negative 25, and then he's turning around and he's going from negative 25 to negative 18. So imagine you're just moving along the x-axis. Each unit is 1 meter. So if we do negative 25 minus negative 9, that's a distance of 16. And then if we go from negative 25 back to negative 18, that's a distance of 7. So I say the distance between here and here is 16, distance between here and here is 7. 16 plus 7 is 23, so total distance . So in the past, I would see students struggle with this, not really knowing what to do with these numbers. So I'm hoping that if you feel like you need to visualize it, then just go ahead and put those numbers on the number line and just count your way through, right? Every step you take is a positive step. So it doesn't matter if you're moving left or right, we're counting each step that you take as a positive value. So if I'm going from here to here, back to here, I'm going to take a total of 23 steps. Okay, last two parts here. Is velocity increasing or decreasing at t equals 2? Careful with the wording here. How do we approach this problem? What's another way of rewording this problem? Okay, not increase, decreasing. Another way to reword it is acceleration positive or negative. Okay, if we include the word increase, that means we're changing it to something below acceleration. So another way of asking this question is acceleration positive or negative? The reason why we're talking about acceleration is because we see the word increase, decrease. Increase, decrease is changing the definition of what's being asked. Okay, it's not asking about velocity anymore. It's asking about the rate of change of velocity, which is really acceleration. So it's misleading because you see the word velocity and you naturally want to use velocity, but this increase decrease changes what is being asked of. So we want to find a of 2. Plug 2 into the acceleration function. That's 2 times 6. 12 minus 6 is 6. A of 2 is 6 meters per second squared. Therefore, that's a positive velocity. Positive velocity means velocity is increasing. Sorry, positive acceleration means velocity is increasing. And then finally, is speed increasing or decreasing? There's a slight change in the word here, and there's also going to be a very different approach. How do we determine if speed is increasing or decreasing? More than that. We have to look at velocity and acceleration and compare the what? Compare their signs, right? So we need to find velocity at 4, find acceleration at 4, look at their signs. If they're both positive, speed is increasing. If they're both negative, speed is still increasing. But if the signs are different, if one is positive and the other is negative, then speed is decreasing. Velocity at 4 is positive. Acceleration at 4 is also positive. The positive signs indicate that speed is increasing since they both have the same signs. Which problem? So for H, I'm just subtracting the distance between these two. So negative 25 minus negative 9 is going to be a distance of 16. And then negative 25 minus negative 18, that's a distance of 7. So I'm going from here to here, which is going to cover 16 units. And I'm going to go from negative 25 to negative 18, so I'm going to walk backwards 7 units. So 16 plus 7 is 23. Okay, that's all I have. Any other questions?
Could you kind of go over like the roles and like what kind of problems to use them on?
Yeah. Sure. What do you mean by that?
Like,
When do you use power rule? When do you use product rule? When do you use quotient rule? Okay. So all right, see you. So if you look at number 1 here, x times x minus 1 squared, the first thing we should always ask ourselves is this possible for me to expand out and completely get rid of the parentheses? I think it's doable, right?
by squared.
Yeah, so I can fill this out. If you can get to the point where all the parentheses are removed, then you should be able to go through power rule.
Power rule? Okay.
But if you see a numerator and denominator, then you're forced to have to go through quotient rule.
Quotient rule?
Yeah.
The power rule is just like kind of taking the exponents and changing them around.
Yeah, so like number 1, if you can do number 1, you should feel pretty good about power rule.